All right, today we are diving deep. We're going right into the heart of embedded systems to uncover some invisible rules, the hidden rules that govern memory. And let me tell you, these are the rules that, when you ignore them, can cause absolute chaos in your projects. So let's get into it.
So have you ever been there? You've got a project that's humming along perfectly for hours, and then bam, it just crashes out of nowhere. Or maybe a peripheral that just refuses to see the data you wrote. It is one of the most frustrating things a developer can experience.
And here's the secret, right? The bug, more often than not, isn't in your application's logic. Nope. It's hiding in that gap between your high-level C code and the low-level reality of the hardware itself. You see, your code makes these promises that the silicon can't always keep, at least not without your explicit help.
So in this explainer, we're going to tackle 4 of these hidden challenges. We'll look at data that just seems to vanish into thin air. We're going to hunt down a silent killer that crashes systems, learn how to draw our own memory maps, and even tame a power-sucking vampire. Let's get started.
Okay, our first case is a total classic. I like to call it the disappearing data problem. This is what happens when 2 different parts of your chip look at the very same memory location, but they see 2 completely different things.
So just imagine this scenario. It's a super common developer problem. Your CPU carefully, meticulously prepares a buffer of data. Then it tells the DMA controller, that specialized hardware for moving data around, to go ahead and send that buffer out. But the DMA sends the old data from before your update. It's as if your changes never even happened. What is going on? Well, the culprit has a name: cache coherency. And this analogy just nails it. Think of the CPU's super fast cache as its own private notepad. It jots down changes there first because it's lightning quick. The main RAM? That's like the public office library. It's a bit slower, but it's the official record. Now the DMA is like a courier who's been sent to pick up a document. Their instructions are simple: go to the library. They have no idea what's on the CPU's private notepad. So the solution is this really crucial 2-step dance. First, before the DMA needs that data, you have to clean the cache. This is you telling the CPU, hey, copy everything from your private notepad to the public library right now. Boom, the courier sees the right version. And second, after the DMA writes new data into the library, you invalidate the cache. This tells the CPU, psst, your personal notes are out of date. Go check the library before you use that data again. It's that simple, but you have to do it.
Our next problem? Well, it's even more sinister. It's a silent killer that causes these random, unpredictable crashes that are an absolute nightmare to debug. We're talking about the stack overflow.
So here's how it happens. A function uses up a little too much local memory, its stack space, and it spills over, just silently corrupting the memory of whatever function called it, or maybe even another task entirely. The crazy part is, the system doesn't crash right away. It crashes later, when that corrupted data is actually used, which makes finding the root cause feel almost impossible.
So how do we hunt this killer? Well, here are the options. The best method by a long shot is using hardware like a memory protection unit, or MPU. It basically builds a digital fence around your stack, and any attempt to write outside of it triggers an immediate hardware exception. It prevents the corruption from ever happening. The other methods, they're not so great. A software red zone only checks for corruption later, after the damage is already done. And the stack pointer check? That is the worst of all. It's like trying to catch a bullet after it's been fired, just way too late.
All right, this leads us to our next tool. What if you need to place data not just inside some boundary, but at a very, very specific location? For that, we need to become the architect of our own memory map, and we do that using linker scripts.
Here's a real-world problem straight from a developer forum. A developer needed to place their Ethernet buffers at the exact memory address 0x2400000. Why? Because the hardware literally demanded it be there. So how do you do that? You can't just cross your fingers and hope the compiler puts it in the right spot.
The answer is the linker script. Think of it as a blueprint, a configuration file. You use it to tell the linker, that's the tool that builds your final firmware image, all about the memory regions on your chip, and then you tell it exactly where to place every single piece of your code and data. Now, I know what you're thinking. Linker scripts can seem really intimidating. But just look at this quote from that same developer after he figured it out. He said, "It's so much fun, so I did it for the UART buffer as well." That's the moment, right there. That's when you go from being just a user of the tools to the master of them. It's seriously empowering.
So really, it all just comes down to control. If you don't touch the linker script, you're basically flying blind, just letting the compiler make all the decisions. But once you master it, you gain surgical precision. You can place a buffer in a special non-cached RAM region or put critical functions in super-fast ITCM memory. You are in complete and total control.
Okay, for our final case, we're tackling an enemy that drains the life out of every single battery-powered device: excess power consumption. We are going to tame the power vampire.
So you've built this awesome new gadget, but the battery life is just terrible. It dies in a few hours when it should last for days. So what's the deal?
Well, the problem is that even when your device is just sitting there, doing nothing, waiting for something to happen, the CPU core is probably running at full tilt, just burning through your battery.
Let's look at a really solid example from an ST application note, a smartwatch. I mean, to be useful, it can't be sitting on the charger all day long, right? Most of the time, that screen is off, and it's just waiting. This is the absolute perfect application for using low-power modes.
Now this is where it gets really interesting. Look at this data. If the watch just uses run mode all the time, it burns through over 19,000 millijoules of energy. But just by adding sleep mode for those short idle periods, that number drops by 2/3. And then when you add in deeper stop and standby modes for the longer waits, the consumption just plummets.
And this right here just drives the point home. By aggressively using all the available low-power modes, basically putting the CPU to sleep at every single possible opportunity, the developers saved 85% of the total energy. 85%. That is the difference between a product that lasts a day and one that lasts a whole week. So, after we've tackled these 4 cases, what's the common thread here? What connects all of this? It's about thinking beyond just the C code and adopting a true embedded mindset, where you become an active partner with the hardware.
So here it is. This is your toolkit for writing truly robust firmware. Control your cache to guarantee data integrity. Protect your stack to prevent those mysterious crashes. Master your memory map to satisfy tough hardware constraints. And manage your power to build incredibly efficient products. These aren't just suggestions. These are the unwritten rules for professional embedded development.
And all of that leaves us with one final question to think about in your own work. When you write a simple line of code, what are the invisible forces, the cache, the MPU, the linker, the power manager, that are really in control of how it runs? Because mastering them, that's the key to mastering embedded systems.